Yes, sir. Okay,
thank you, Jose. Good evening, everyone. Welcoming you all to the 42nd session on Vertical 3. As you all know, we focus on practical sessions on open and proprietary softwares. Today, the session will be by ChemAxon from 6 p.m. to 8 p.m. Myself, Giri, one of the coordinator for Drug Discovery Hackathon. As usual, disclaimers, please do not share any personal details, including your email address, during this online meeting in the YouTube chat live. If you have any queries on registration, official registrations, you can write to ddh@aict-india.org, and any queries related to virtual tool room, accessing partner softwares, or even CDAC servers, your queries could be routed to DDTR support@cdac.in. All of you kindly type your questions in the live chat, and during the Q&A session, we will try to answer them. And this is how the DDH virtual tool room form looks like. So you can choose one or many softwares, or if you can opt out, and then the partners will contact you directly for how to get access to the tools. So today, I'm happy to introduce two speakers from ChemAxon on the topic. Today, they're going to discuss on the topic, building a drug discovery workflow in 8+1 steps with KNIME. So first, I'd like to introduce Dora Barna. She received her MSc in chemistry and PhD in theoretical chemistry in 2013 at the University of Szeged, Hungary. She joined the development department of ChemAxon in 2012 as a business analyst, where she took part in the planning of development of multiple ChemAxon software products. Later, she joined as an application scientist team to the team of ChemAxon, where she is responsible for supporting clients in designing cheminformatics solutions and for conducting application studies. And when we are going with Norbert Sass, he's the head of consultancy services with ChemAxon. His team is devoted to solve integration, customization, and migration-related problems. Graduated as chemist and pursued his academic career in quantum chemistry for few years as researcher. Norbert joined ChemAxon 7 years ago. Prior to his current role, Norbert was a product owner of Compliance Checker, a product that has been fully redesigned to achieve a speed boost of 100-folds. He contributed to the development of ChemAxon search engine as a business analyst, and in his free time, he enjoys aquascaping. So we have two wonderful speakers today. Over to you, Dora, and we are looking forward to the session online. Thank you. You can now share your screen.
Okay, thank you very much. Thank you for the introduction, and welcome everyone for this session of the Hackathon series. So my name is Dora Barna, and today I would like to share with you and introduce you this drug discovery workflow that we have built in KNIME using ChemAxon tools. So first, who we are and what we do at ChemAxon. So we provide software solutions and services to enhance drug discovery and other chemistry-related fields with chemical and biological intelligence. If you want to categorize the tools and services that ChemAxon provides, then we say that in the first category, we find solutions and toolkits which help us recognizing and extracting chemical information from a variety of sources, from documents, spreadsheets, databases, and so on. In the second category, we find those tools which are the most helpful for chemists who are working on and with and designing new chemical compounds. In this category, we find our chemical sketcher solutions, property predictors and calculators, virtual library enumeration tools, as well as clustering solutions and several toolkits for working with Marcus libraries. While in the third class, in the third category, belong those tools and cheminformatics applications, which are the most helpful for those people who want to build a chemical structural database from their compounds and who want to search and browse such databases. Among these tools, we find various chemistry cartridges and tools which help with checking and standardizing the structure of various molecular types. How can we access this functionality from KNIME? There are two different approaches that we can take here. The first approach is that ChemAxon, together with our partner company called Infocom, developed a set of dedicated KNIME nodes with which various parts of the ChemAxon functionality can be accessed. These ChemAxon Infocom nodes can be used, among others, to draw molecules, reactions, query structures, Marcus libraries, and also to visualize these chemical structures in KNIME in different formats. And the other parts of our cheminformatics toolkits, like the property predictors, the structure search engines, the library enumeration tools, are also available via this dedicated node collection. As you will see, we have separated this node collection into two parts. The first one contains the Marvin extension, so the chemical sketcher and the chemical visualization toolkits, while the second larger part, the JChem extensions, contains everything that one has to use to calculate properties, to build and search in a database, or to interact and manipulate chemical structures in different ways. So this is the first approach via the dedicated KNIME nodes. The second approach, how ChemAxon software can be used from KNIME, is useful in those cases when one of our server-based components are needed in a KNIME workflow. Because KNIME has these native REST web services nodes, and via these REST web services nodes, our different web-based solutions can be accessed and integrated into a KNIME workflow. So this way one can use, for example, a biomolecule toolkit to interact with macromolecules and different biomolecules, but also our large-scale similarity search solutions, physicochemical property calculations, database management toolkits can also be plugged into the KNIME workflow using RESTful web services. Here you can see some examples of how our Marvin extension nodes can be used. As I've mentioned, one of the most popular part of our KNIME node collection is the Marvin sketch node, which can be used to draw any kind of chemical object, which can be an exact small molecule, or a generic structure, or an entire reaction with the additional data and mapping of the reactants and the products. And besides using the Marvin sketch node to enter this chemical structural information into the KNIME workflow, the Marvin extension node collection also contains items which can be used to visualize structural information in to display the results of the KNIME workflow. And the second group, the JChem extension nodes, as I mentioned, contains a larger part of the ChemAxon functionality. We can find here nodes to convert between different chemical file formats, or to manipulate our chemical structures, to calculate their properties, store them in a database, check and standardize their structure, or to cluster them, or generate a virtual compound library in order to get a large set of virtual molecules to work with. So, and with these two node collections, a wide variety of cheminformatics workflows can be built in KNIME, and chemical intelligence can be injected in generic data manipulation and data analysis workflows. Now, let's see what the workflow that we planned for today, that we plan to share today, looks like. So our goal today would be to share with you a workflow where we start from a set of known biologically active molecules, a set of known CNS active molecules, and we would like to use this workflow to generate at the end a set of novel compounds which are promising enough, meaning that has good physicochemical properties, are easily accessible, and have potentially good biological activity. So our goal is to generate a set of such promising molecules which we can use as potential new test compounds in our biological assays. So the starting point of our workflow is this set of known biologically active molecules which have already been tested against some target protein which can be found in the central nervous system, and we would like to end up with a novel set of compounds which potentially have similar good biological activity on the same target. So how the workflow looks like: first, we will have to import this known set of CNS active molecules, and just like with any other data manipulation workflow, after importing our input data, we have to take care of the data cleaning and standardization tasks. And in this particular case, we have to standardize and normalize the chemical structure part of our input data set. Once we have done this and have a consistent, standardized chemical structure collection, we will use this structure collection to cluster them in order to be able to select a good chemical scaffold, a good core structure, which we can later on use to build a virtual compound library from it. So from the original scaffold, we will build a set of new virtual molecules. And in order to select those virtual molecules which have the potential to show to access our selected biological target, we will filter down and narrow down our virtual compound library collection, and to keep only those virtual molecules which have good physicochemical properties, which will probably allow them to enter the central nervous system and get access to the target protein that we would like to work with. For this physicochemical property-based filtering, we are going to use the CNS MPO score, which can be a good screening, virtual screening solution in order to find those compounds which have a potential to cross the blood-brain barrier and get access to the central nervous system. So once we have done this, we will have a set of virtual compounds which have physicochemical properties that fall in the desirable property space. Now the next step would be to further narrow down this virtual compound collection and keep and find those molecules which we can access easily. This means that we have to either analyze which compounds are accessible, which compounds can be readily bought from some chemical vendor catalog, or another option could be to analyze which compounds are easy to synthesize. We will take the first approach here. So we are going to take these remaining virtual compounds and look for structurally very similar real compounds that we can readily access from vendor catalogs that offer real compounds for us. And once we have switched from this virtual space to the real, readily accessible chemical space, we will filter again these real analog molecules that we have found using again the CNS MPO score-based filtering, just like in the previous step. And now we will have real accessible molecules with good physicochemical properties. So the only thing that we will have to analyze before we can make the decision of which novel compounds we would like to work with, which novel compounds we would like to synthesize next, is to have some kind of indication that which of these real analog molecules have good biological activities, which molecules can we expect to have a good interaction with our selected target protein. And for this, we will use, we will build and then use a classification, a predictive classification model, which will give us some predictions whether our real molecules can be expected to show biological activity on our target protein or not. And at the end, we will get molecules which are novel, have good physicochemical properties that we need for our project, which are easily accessible and which have good chance to show real activity against our target protein. Here on this slide, you can see how the very same workflow looks like in KNIME. And this is the workflow that in the second part of our presentation, my colleague Norbert will show you in much more detail, and will tell you about how they come together and how they can be configured to do this step-by-step filtering and compound selection. Before we go there, let me give you some overview and insight into the main steps of the workflow. So the step one is where we import our data, where we get the input data into the workflow. As I mentioned at the beginning, our input data is this case a set of known CNS active molecules. This set contains more than 3,200 compounds, each taken from the Campbell database, and each of these molecules were tested against the human dopamine D2 receptors, which means they have a p-Campbell value in the Campbell database. So these are the known CNS active compounds that we would like to start working with, and at the end of the workflow, we would like to end up with new novel compounds that can be expected to show similar activity. So to import this data, we are going to use the mol importer node from the ChemAxon Infocom collection, which can be used to import an SD file, like in our case, or it can take care of importing many other chemical file types also. Once we have imported the input data into our KNIME workflow, the next step would be about cleaning and standardizing this input data and pre-process the structures to make them ready to the upcoming clustering and library generation steps. For this pre-processing, the key item that we are going to use, the key node that we are going to use is our standardizer node, which can be used to normalize chemical structures. After that, we are also going to calculate the molecular weight of our inputs, of our standardized input molecules, and generate their SMILE strings. And as a last step in the structure pre-processing, we are going to use the generated SMILE strings to do a duplicate filtering on our standardized input data collection. A couple of words about the standardizer node and the structure normalization. As you will see, the standardizer node offers various structure standardization actions which can help us to get a consistent, normalized structure collection. So this can mean that we can decide to aromatize every imported molecules, to strip the salts or any other small fragments from them, remove any explicit hydrogens, take care of tautomerization issues, neutralize compounds, and so on. Or we can also transform typical functional groups, for example, nitro groups, to have a single consistent representations for each molecule that contains this functional group. And once we have these pre-processed and cleaned input data in the workflow, we will continue with clustering this input molecule collection. And we are going to do here is a hierarchical clustering step in order to be able to select a scaffold from our input data collection. And this scaffold, this core structure, will be selected based on the criteria of what is this scaffold structure that appears frequently in our input data set, and besides being a frequent scaffold in the input data set, it should also have a good average biological activity, a good average pKa value in order to select it for our core structure on which we will build our virtual compound library in the upcoming steps. So that the key item in our clustering part is the library MCS node. Again, it can be found in the JChem extensions node collection. This library MCS node can do hierarchical clustering, looking for the maximum common substructure of the input molecules. You can see how this maximum common substructure looks like for two compounds which were taken from the input dataset. And the library MCS nodes looks for these MCS structures among each pair of the input molecules, and then hierarchically it goes to the next level where it will search for the MCS structure of the previously generated structure sets, and so on and so on. So at the end, it will give us scaffold core structures which represent a large enough part of our input data set. And once we got these clustered, hierarchically clustered version of our input data set, we were able to select the most frequent and the most active scaffold from the collection. So once we did this scaffold selection, we wanted to see how these scaffold in the input data set is typically substituted, which part or which atoms of the selected scaffold are the most frequently substituted, and what kind of functional groups can be found in which positions. And what we got from this analysis is that the two ortho aromatic carbon atoms were the most frequently substituted points of the scaffold molecules, and besides those two aromatic carbon atoms, also the piperazine nitrogen was substituted frequently. So with this information in mind, we were able to plan and design our virtual compound library for the next step. So what we wanted to do is first to generate compounds where our selected scaffold is substituted in the two aromatic ortho positions, and then we also wanted to functionalize the piperazine nitrogen. To achieve this, we used virtual reactions and virtual reaction-based library enumeration. For this, we used three different reaction schemes. First, in the ortho substitution, we used two different reaction schemes. One of them was a nucleophilic aromatic substitution, while the second one was a Friedel-Crafts alkylation of the aromatic ring, and then concatenating the result sets in order to get a larger collection of substituted aromatic aromatic compounds. And after this ortho substitution, we also use the third reaction steps to functionalize the piperazine nitrogen. But before going there, let me show you how we did this virtual reaction-based enumeration. We used for it our bimolecular reactor node from the JChem node collection, where we took our selected scaffold and then imported a set of building blocks or substituents, which we could use first in the nucleophilic aromatic substitution reactions. And with our selected scaffold and the imported building blocks, we could use the reactor node to run virtual reactions, virtual transformations, where we had to define a generic reaction schema along with some reaction rules, for example, to have some rules for the selectivity of our reactants. And as a result, the reactor node generated for us the virtual products of our selected reaction schema. So after we did this with the nucleophilic substitution, we repeated the virtual reaction with Friedel-Crafts alkylation type of transformation as well, where we imported another set of reactants and virtually reacted them with our selected scaffold again. So from these steps and from concatenating, then we ended up with a collection of virtual substituted aromatic systems. So what was left to do is the third reaction step, where we wanted to functionalize the nitrogen in the ring, in the other ring of the scaffold, and for this we selected an alkylation reaction schema, where again we used the same reactor node with another generic reaction scheme and another reaction rule set to make the transformation more chemically meaningful, and as a result we got our functionalized virtual compounds. Now these virtual compounds can be really huge after just a few reaction steps, and in order to select the really useful ones which have the potential to be useful in a central nervous system related project, we had to do some virtual filtering. And a typical way to do that is use the predicted physicochemical properties to filter these generated virtual compounds. So our goal here is to find virtual molecules which have a high chance to cross the blood-brain barrier in order to get access to the dopamine D2 receptor, which is our selected target. And crossing the blood-brain barrier and the ability of a molecule to do that is influenced heavily by some key physicochemical parameters. For example, the scientists at Pfizer found that there are 6 physicochemical properties which have a key influence on whether a molecule will be able to penetrate the blood-brain barrier or not. So once they came to this conclusion, they created the so-called CNS MPO score, which is a weighted scoring function that assesses these 6 key physicochemical properties. And these are the CNS MPO score and the underlying 6 physicochemical properties that we are going to use for this filtering that we want to do. Here you can see how we will progress. So after generating the major tautomer of our generated virtual compounds, we will calculate the molecular weight, the log P value, the log D, the polar surface area, the number of hydrogen bond donor atoms, and finally the strongest basic pK values of our enumerated virtual compounds. And once we have these predicted values, we will transform them using different transformation functions in order to get a score contribution from each of the 6 physicochemical properties. So in order to get the score contributions that are needed for the CNS MPO calculation. And once we did the transformation for each predicted and calculated PhysChem value, we will add them together in order to get the final CNS MPO score value. And once we have this MPO score for each virtual molecule, we can use those values to filter our compound collection and keep only those virtual molecules which have the highest or high enough predicted MPO score. So with this, we can narrow down our virtual library quite significantly as well. So, and this way we end up with molecules which have good enough physicochemical properties. Now the next question that we have to answer is how can we use these good virtual compounds to find equally good but real and accessible compounds. One way to do that is to use a large-scale similarity search, where we use our remaining virtual compounds and search with them, use them for similarity searching in large databases that contain real existing or easily synthesizable molecules. One of such large databases is the Enamine Real database, which contains easily synthesizable or readily accessible compounds. And in our workflow, we use a subset of this Enamine Real database containing 170 million compounds, and we use our MedFast similarity search tool to do a large-scale in-memory similarity search, where our goal was to find structurally similar analog compounds for each of our remaining virtual molecules. As you will see in KNIME in the workflow, we built in the MATFAST functionality using web service calls and using the native RESTful nodes of KNIME to send post requests and GET requests to the MATFAST server applications. And as a result, we got a set of readily accessible molecules where again we did a duplicate check to have only unique compounds in a collection, and this way we had molecules which can be prepared or can be readily bought, but are structurally very similar to our most promising virtual compounds. But in order to make sure that these found real analog compounds have really good physicochemical properties, we repeated the CNS MPO score-based filtering on these real analog molecules as well to filter out those ones where the physicochemical properties are not good enough. And after this filtering, the next step was to get some kind of prediction for the biological activity that we can expect from these remaining analog compounds. And to have this prediction for the biological activity, we built a predictive classification model, which later on we can use to categorize, to classify our enamine analog molecules as active or non-active compounds. This binary classification model was built using the random forest algorithm, which can be accessed from the generic KNIME nodes as well. And the model was built based on the original CNS active compounds that we used as our input, also at the beginning of the workflow. So based on these molecules and using these molecules and their p-Campbell values, we were able to build a binary classification model with the random forest algorithm. And this model that we built, or by building the model, we used the ECFP fingerprints of the input molecules, again from the JChem extension collection. And once we had the model built, we also checked the accuracy of it, and then we used the accuracy values you can see here in the confusion matrix. So the model, the predictive model, had an accuracy a bit larger than 83%. And once we have built this classification model, we used it to predict the activity class or the active or non-active state of the input or the remaining enamine-based analog compounds as well. So what you can see here on the right are the remaining enamine molecules where the color code tells us if a molecule was predicted as active. These are the compounds with the green label, or whether a molecule was predicted as non-active by the model that we built. These are the red compounds. So this way we could also visualize these compounds, visualizing these calculated CNS MPO score and their predicted active or non-active state. And in one of the interactive chart notes of KNIME, we were able to do a visual selection to keep only those molecules where the CNS MPO score is high enough and the molecule was predicted as active. And with this selection, we could answer the question of which molecules should be synthesized next, what are the most promising compounds that should be tested in the next phase. So these are the 8 core steps of the workflow, and the step +1 that we also built in into our example is about checking the overlap, the structural overlap between the enumerated virtual space of the molecules that we generated and the real space that we found with the MetFirst search in the enamine real database. So if we do this overlap analysis, we will be able to see how large is the dissimilarity between our enumerated virtual compounds and their real analogues that we got from the enamine database, and we could we will have some information this way about whether we are really exploring a new part of the chemical space, how far away we got from the space of the original virtual molecules. And as you will see at the end of the KNIME workflow, what we did here is an interactive visualization where we wanted to display the distance between the 2 chemical sets, the virtual chemical set and the real compound set. And for this, we calculated the structural dissimilarity between each virtual molecule and its first, 5th, 10th, and 20th nearest neighbor. And we visualized each of these 4, the distribution of each of these 4 structural dissimilarity values in a histogram in order to see whether we are really, whether we are still close to our original virtual space, or if we could get a bit further away from it and explore a novel part of the chemical space. So this is how the workflow will end. This is where we would like to get. And with this, I would pass the word to my colleague, Norbert, who will show you all of these in much more detail in KNIME. So Norbert, the stage is yours then.
Hi, Norby. I guess you are muted.
Oh, sorry. Okay, yeah. Sorry. Yes, can you hear me now?
Yes, I can hear you now.
Fantastic. I'm sorry. Yes, I was muted. I'm sorry for that. So, welcome everybody again. I was speaking in the meantime without noticing this error. So, first of all, let me just present you a little bit the KNIME, so the tool that we are going to use today, or Dora already presented, and which is basically a very good and very intuitive workflow tool. The way it works is basically that you have your projects on the left-hand side panel, and you have a canvas where you basically write your little program and workflows. Here you can drop so-called nodes. And if you connect, you can run these nodes. And if you connect these nodes, there is going to be a data connection or data flow between these nodes. So basically, you can meaningfully process data with this. So let me take a very simple example. Here, there is an SDF reader. So there is a structure file somewhere on my computer. I can configure where that is. It's right here. And I can, of course, run this one. And what I can do with this is that, for example, for those molecules that I have in that file, that I've read, I can calculate the pKa value for that one. And here is where you have basically the nodes that you can select from, and you can extend the number of these nodes with proprietary nodes, so it's something that you can buy from vendors, or some nodes actually that are freely available on the market in the world. So what I was doing is just dropping here the pKa predictor, and if I want to see what is the output of a node, it's very easy because I'm just going to the bottom of this context menu, and I want to visualize what are all the molecules that I read up from this file. And as you can see, this is my first molecule in this file. I have in total 462 molecules in this file. So what I want to do with this is to link the output of this as the F reader to the input of the pKa predictor. If I double click on that one, you will see that there are a lot of options that you can set. We are going to use this one further down the road when we are going to talk about the drug discovery workflow. But for now, I'm just going to present you that basically with the default, you can click execute, and this node is going to execute its work in some minutes or seconds rather. And I'm sorry, this is my computer that is loaded with a lot of stuff. And if you want to look at the result, here you have the results. So where you can see that new columns have been added to the initial set of columns that was there, and you have pKa values in this table, so to call. Okay, so that's how much I wanted to tell you about the tool itself that we are going to use today. And let's get back to the workflow that we would love to dive a little bit deeper into. Remember, what is our problem that we want to solve? First hand is that we have a set of molecules, as Dora put it. We generated those ones from Campbell database. We know that they're active on the dopamine D2 receptor. And from these molecules that everybody knows that they're there in the world, we want to generate new novel molecules, which we think might be also active on this very same receptor. Okay, the way we are going to do that is exactly how Dora explained it. But let's see on the programmatic level, how do we do that? We have a mole importer, which does basically nothing else but loads the SD file that we have, and we filtered from the Campbell database. It has a little bit above of 3,200 molecules, and we also have the p-Campbell value. You see, this is a beautiful number for that one. Okay, so we have the set. The first thing that we do with these ones is to somehow get them to the same representation. What do I mean by this? With chemical entities, you might probably know that sometimes we as chemists, we draw different molecules that are exactly the same in different ways. And this is what standardizer is very good for. For example, to transform the nitro group into something that's always the same. Okay, so if somebody draws the nitro group like this, then we are going to transform all of those to this representation just because we chose this one as a convention to represent the nitro groups. You can choose anything. But the aim here is to have all of the nitro groups represented in the same way. Okay, what we also do here in this standardizer is that if we were to have such records in this list which have salts, like, I don't know, potassium, sodium next to them, which is very likely because we are talking about drug-like molecules, then we want to strip those ones. We don't care about the counterions, we care about the active molecule, right? So then we apply salt stripping. We have we are gonna mine the tautomer form, so we are gonna actually transform all of these molecules to their main tautomeric form, and then finally we are going to aromatize all of these structures. You see, between, next to the nitro, you have acid, diazonium, sulfone, and other transforms exactly for the same reason as for the nitro, to have them represented in a very same way. So if we run this, the output is going to be the so-called standardized molecule. And okay, I want to show you how do they differ from each other. Well, in this case, not very much. Actually, we were doing tautomerizations, but in this case, for example, if I can make this bigger in a way or the other, please help me. Okay. Then you can see that here in this molecule, we had a hydrochloric variant of the active molecule. And because of the salt stripping, we strip this hydrochloride next to it. So actually, we are with this main molecule now in a standardized format. It's an aromatic form. Everything looks okay and fine. So we did that first part. Then, as you saw, actually, we had a lot of columns generated by the standardizer, which you don't really need. So we will basically need just a very few of them. So with a filter, with a column filter node, you can filter out those columns, that data that it's not interesting for you. So that's exactly what this node does. And if you look at the table, more skinny, we like it better. We know what we do with that. Then we want to calculate the mass of the given molecule. That is super easy. So we just add a column which is called mass. The configuration for this one in the elemental analysis node is pretty easy because you can just tick and execute that kind of calculation that is interesting for you. Based on the molecules, based on the standardized molecules. Okay, we selected here the mass and the formula. You're going to see why that's interesting. It is interesting because with the advanced mole converter, we want to convert all of the structures, all of the standardized structures into the SMILES representation of those ones in order to be able to de-duplicate the set of structures that we have, right? Because we executed a standardization, and because of the standardization executes some chemical transformations. So maybe in the original file, we had two tautomers of each other, but now because of the standardization, both of them are represented in their main tautomeric form. Therefore, there we expect that their SMILES is going to be exactly the same. So if we run a deduplication with this on the SMILES column, on the SMILES field, we are going to get somewhat less data. So just 3,251. So indeed, we filter out some duplicates. Very good. With this one, we finished this step of clearing the data for later data analysis. The next one is the hierarchical clustering for scaffold selection. So what do we want to achieve here? It's basically that we want to get a scaffold, something that is very, very often showing up in the original set that we know it's active. Take that scaffold and try to decorate it a little bit later. So with that one, with those decorations, we can generate supposedly or hopefully new molecules. But first of all, we have to identify what is this scaffold that we have to work with. And this is why we used the hierarchical clustering as a good method for this. And for that one, as Dora already showed you, we use the library MCS node of ChemAxon extensions. What this node in reality does is, remember, as Dora said, and let me check and show you that that slide that she was presenting, it is that the algorithm is looking for scaffolds which are common between the whole set, those 3,251 molecules in this case, and we can restrict a little bit the algorithm, as we can tell the algorithm that please take into account structures that are bigger than 12, at least 12 heavy atoms. So otherwise we would get just a simple carbon atom, right? Then that's not what we want to get. We want to get a meaningfully big structure and scaffold. Then you can also define what kind of other parameters should the algorithm take into account: atom types, bond types, charge maybe, and in this case we did not take into account radicals or isotopes. And then you can also say that, okay, the maximum level count, you can limit it to 10, and the required cluster count in our case was 1. So if we run this on the data set that we have, it is very interesting. So it is gonna identify you some cluster ID with some molecules, which is the maximum common structure in this case. And it will also tell you that the element count of this hierarchical family is 50. So what you can do with this is basically, as a first, for the first site, you can order this and say that, okay, I want to check actually which is my biggest family, which is that molecule actually that has the most members. Therefore, it's more often present in the set. And I want to show you this one. It's just that my mouse is not willing to show you that. So it's basically this molecule that's gonna be. So now we visually know which is the one that we need to select. But what we wanted to do here in this workflow is to do it by algorithm, right? And basically the chemical question is already answered here in this workflow. You know what you're looking for. What is the scaffold that you want to use? Especially if you're looking for the second molecule, that is just like, I don't know, 30% less frequently present in the database. So all the rest is basically just juggling with the data and data transformation to do this selection in an automatic way. How do we do that? First of all, we need to get somehow the we need to interpret somehow the hierarchical the information that we got from the MCS library. And then we want to select only those items actually that do have a recovery ID. And this is something that we can do with a row filter node. The row filter will exclude rows by attribute value. We are examining the recovery ID field in the data. Let me show you the data so it will be obvious for you what are we looking at. So here we have the recovery ID, and in some cases we don't have data for this, right? And we want to filter out those ones. The way we do it is that we go to the row filter node and we say that we want to exclude only all of those rows which have missing values. Okay, if you run these ones, naturally you're going to have a list of less compounds. Well, yeah, there are still a few here. And then we want to somehow interpret the top level, the clustering information. And for that one, actually, we have to extract which is the top level cluster and what is the information there. There we are using a very interesting node and might not be that very interesting from chemical perspective, but from programming perspective, it's an interesting node. What we can do here is the hierarchy ID. So let me show you again what the original data looked like before entering to this node. The hierarchy ID looks like this. It's a number dot a number dot a number dot a number. And that is actually what defines your hierarchy. So what we want to do here is to select the top hierarchy. So that molecule which actually belongs to the top hierarchy. And for that one, actually, we need to split this 1.1.1.1 thing. And that is something that we can do with the cell splitter node. So we say that we want to analyze the hierarchy ID column. The delimiter is a dot. And that's what we want to do. The output of this one is gonna be not very surprising. The first one, second one, third one, fourth one, and the fifth one without dots in between. So what we are gonna be looking for, we wanted the first one because that's what stands for the top level hierarchy. So we are gonna select on this, we're gonna filter on this data field. That's what the column filter exactly does. We threw away all the other columns because actually by now we had quite a few, and we keep only those ones which are meaningful for us. So let me get back, and then you're going to see that what we are going to end up with is a reasonably short amount of data where we have these hierarchical data too. The next one we want to do is to group all of the structures based on this top level data, and also, as Dora said, to, well, take into account something else that is also interesting. And this is the node actually that stands for that one. So we are going to be selecting the hierarchy ID. And if we execute that grouping, you're going to see that the first one has like a count of 50, and the mean mass and the mean P, actually the mean mass does not really mean here too much, but the mean P Campbell value might be something that you want to look for. Okay, so then we need to convert a number to string, because then we want to compare these two to each other. So we are going to have the count and the hierarchy ID converted. Why do we do that? Because our next node here is a joiner. So in the next joiner node, we want to join this subset of the data with actually original data that is a little bit filtered. And in the filter, we are filtering on the parent ID of this one. So we are looking for those elements where the parent ID is 0. Why exactly 0? Because that is our first fragment, so our first MCS, the MCS actually that shows up the most times for that, and that is what we want to join with this set of data. Okay, so we run the joiner. The joiner is going to be running and pairing the hierarchy ID with the hierarchy ID array 0. You know, this is the one that we split, and we are going to use an inner join to join this. Here, of course, you can choose other joins too if your problem is different. Well, in this case, we needed an inner join. So if we run this one, we are going to have a table of 123 molecules that actually hold a lot of hierarchical data about themselves. Okay, the rest I'm not going to really discuss in high details. Here we have a sorter that's a different kind of node. Naturally, we are going to just look for those, we want to sort the data. So basically we want to look for those fragments or those MCSs for which the element count is the biggest. And in the meantime, we are also kind of interested in the mean P Campbell value, because that is what actually shows us the activity. This is still the original data that we had from the original data set. So if we have that sorter, then easy enough, the first record that's going to show up is this one, which had 1,077 elements in it. Remember, it was the same as we saw visually before. And then we need nothing else, actually, just to have a row filter, which actually takes out the first row from the data set. Let me show you. That's going to be a very complicated table. And this is the guy that we selected for this use. Okay, so with this one, actually, we have the hierarchical clustering, and all at the same time, we also selected our scaffold that actually shows up most frequently. And that is exactly the one that Dora was showing you in the presentation, but here I'm going to also try to show you. So that is that guy. I hope it's familiar for you. Okay, let's go for it. So we have the scaffold. Our next step would be to decorate this scaffold, right? So we want to generate new compounds using this scaffold by decorating it in a different way with different reactants. And for that one, we wanted to get some ideas how to do that and where to do that. And that is what we actually gained with the R group decomposition. As basically the R group decomposition has an input of basically the structures, and the output looks like, oops, this was open in a different window, so let me try this here. So what you can see here is that basically we have the scaffold. This is the original molecule. We have the scaffold, and we have some additional substitution on different parts of it. How many substitution places do we have? Well, it's very easy, because if we look at actually the structure of our table, we can see that actually 14 ligands have been identified. It means that actually there are 14 places where we could probably decorate this scaffold. But also, if we get back to these ones and to check the table, we are going to see that many of these ones are just hydrogens. Well, it's not very surprising, right? But some of them are interestingly different. And if you just scan through this visually, you're going to see that basically there are 2 or maybe 3 ligand places which are different than hydrogens in this case. And those places are exactly the ones that Dora was talking about, which is basically the nitrogen from the piperazine ring and the ortho position of, the 2 ortho positions of the aromatic ring of the scaffold. We also went a little bit further because we wanted to know actually how diverse the substitution are, the substituents on these ones. And this is what we did in this node. Again, we do standardize those ones. And at the end of it, we are going to have a list of those substituents that are present. And I also want to show you the structures and how do they differ from each other. So here you see the scaffold. Here you see the scaffold, and here you see actually which is the ligand actually that was associated to this scaffold. So if you were to sort on the ligand, you would have a good idea actually what are the typical ligands showing up on one part of the scaffold or on the other part of the scaffold. So this was the one actually that I was showing to you regarding to the piperazine nitrogen, and naturally you can play the same thing for the ortho position of that aromatic ring. And here, if you look at the result, you're going to see that you have still the same scaffold. And not very surprisingly, the OH is one of the main ligands that show up on the ortho position of the aromatic ring. Okay, so from that one, actually, we gained some extra information, but that is just for our curiosity. In the algorithm, we do not include this information. In return, what we do is that from this R group decomposition, we got to the conclusion that it is basically this scaffold, and this scaffold should be decorated in basically two places: the ortho positions and the nitrogen on the piperazine ring. Okay, so let's do it. That's our next step. Good. How do we do that? We need to play reactions with this scaffold. Okay, the first one that we checked is the ortho substitution of the aromatic ring. And as Dora presented you, here we chose two ways of doing it. One is a nucleophilic aromatic substitution. The other one is a Friedel-Crafts substitution. And for this one, we are using our reactor. Okay, in the reactor, basically, as Dora already said, or presented you, we have the reaction defined. And in this case, as it's a nucleophilic aromatic substitution, it's important for us actually to add some extra rules that can be given, which in this case is basically a selectivity rule that you want that carbon atom actually really to be nucleophilic, and that's what you're checking against with this rule. Okay, you can also define exclusions, or you can define reactivity, as we will see it a little bit further down the road with other reactions, with the alkylation. As Dora said, you can even draw your reaction here, or you can even import it from an MR or whatever format you store your reactions. And again, Dora already mentioned you that you can even play it in the combinatorial or in sequential order, depending on what you want to have and what is your set of reactants. If you have multiple reactants for the reaction, you might want to look for the whole combinatorial space that is defined by these ones. Okay, so this is roughly what I can show you regarding the reactor. But as you might have noticed, and as you might probably know from your chemical studies, the nucleophilic reaction works with a halogen. So originally, if you go back to our data set that comes here, even one further down the road, it might have some halogens, like the scaffold, but in this case, the scaffold does not have. So what we need to do here is to add it. And the easiest way to do it is to use a standardizer, and the standardizers have these actions. And for example, you can just define that you want to play a transformation on all of your molecules where you basically add a chlorine, right? And if you play that action, and if you apply that to all of your molecules, then you're going to have as an output a scaffold that holds a chlorine on it, on the ortho position, right? So we kind of prepared our first part of we prepared one of the reactants that we need for the reactor. The other reactant is coming from prepared as the file that we prepared for this purpose, and those are not that very surprisingly simple reactants that you might have on the shelf of your lab. But here we are still on the virtual space. So if we play the reactions, then we are going to see that naturally this substitution has been executed, and you have if I can show you, yeah, the structure, you have them bound to the ortho position of the aromatic ring. Okay, so with that one, actually, we had some nucleophilic substitution. We can play exactly the same thing with the Friedel-Crafts reaction too. Here, our standardizer transform will be a little bit different, right? Because what we need here is a bromine. If you do not know what these H1X3 stands for, then actually that's very deep in the cheminformatics domain. It stands for it has to be substituted with one hydrogen, so this nitrogen should have one nitrogen bond to that, and actually the valences of this nitrogen are to be 3. This denotation is pretty widespread in the cheminformatics world. So if you get a little bit scared of this one, don't be. It's super easy to understand it. It's just that probably you did not meet it yet. Okay, so that is what the transform does in this case. And naturally, we also have, again, some reactants. I hope I can show it to you. But they are showing up in another. And those are chlorines. Very simple molecules. Again, we didn't want to complicate this one, but naturally, you can imagine that in the real world scenario, these reactants can go even wider than this one. Then we play the reaction. We have the two products in this case, naturally. And lucky enough, actually, we have them in 2 columns, so it's easy actually to work with them. And then we have what we wanted. Okay. So then we need to go to the standardizer again, and we need to take off this bromine from the nitrogen that we had previously on the molecule. So after we took that off, then we can filter for the columns and basically have only the scaffold and the product molecule, and that would look like this. And basically with this step, we already played the Friedel-Crafts reaction, as you can see. Well, this is not the most interesting molecule, but you imagine this happening. Okay. So then we want basically to concatenate these two basically molecule or reaction pathways, and from the concatenation of these ones, we are gonna end up with 27 different product molecules that all aimed actually to decorate our aromatic ring in the ortho position, right? We just played it with Friedel-Crafts and the nucleophilic substitution. Good. So we executed now the ortho substitution. Now we have to go back to that nitrogen which is on the piperazine ring, and we are going to play exactly the same. Here the difference is a little bit is that for this reaction we need to kind of prepare a little bit our second reactant. So we have the terminal nitrogen already in our scaffold, but the reactants might need to be a little bit prepared. That's what we do here with the mole importer. Here we import a set of molecules that are, in this case, much more varied and more creative than it was in the first case. And we also want actually to filter out for really big reactants, because for really big reactants, and we also want to filter out those reactants where we have like, as you can see here, like consecutive 3 nitrogens. because that is going to actually play a different role in such a reaction that we put here in the reactor, and we don't want to contaminate our reaction with that reaction path. If we play the reaction, and here actually the rules are going to be interesting, because here we have reactivity rules instead of selectivity, which here is also something very straightforward, that the signal with electronegativity on the atom should be taken into account for the selectivity, and the reactivity rule can be read here. So these are basically those extra things, extra filters that you use for a reaction in case of a reaction, to have exactly those products that you as a chemist would expect to have. So if we play this, then we are going to have a set of 280 products. Let me try to show you again what are these products. And we can see our scaffold here. We can see that it's already substituted on the ortho position. And then we have the substitution of this guy also on the nitrogen of the piperazine ring. Very good. And this is what we wanted actually to achieve. So that's very good. Then we still have some a lot of columns. We want to filter out some columns because we don't need them. Well, in this case, only one. And we want to rename that one to virtual compound, just so we can kind of find it and identify it easier further down the workflow. Okay, so where we are now, we started from a set of structures which are active. We somehow deduce a scaffold that is based on the maximum common structure of those structures that we know that they are active. We found that these scaffold that we have with the piperazine ring and an aromatic benzene ring on it is the most often showing up structure in that set of structures which are active. And now basically we already took that scaffold and decorated it with some reactants in those positions where we observed that actually the decoration can take place, and usually they are different from a hydrogen, right? So now we have a set of virtual compounds already here. What we now need to do about those ones is to find out whether they are likely to be penetrating the blood-brain barrier. And for that one, actually, we are going to use the CNS MPO score based filtering, and which is basically very easy. We need to calculate all of the physicochemical properties that are needed for this analysis. And if we go back to the presentation that Dora showed us, these are the guys that we are thinking about, right? We need to calculate basically the mole weights, the log P values, log D values, total polar surface area, H bond donor values, basic pKa values, and somehow we need to squeeze their values into functions, which are very nicely denoted here or visualized here. So let me get back to the KNIME workflow and see how we did that. Well, first of all, we have to calculate all of these properties. Nothing's easier than that. We have a bunch of molecules coming in. We do tautomerize those ones to their main tautomeric form. The output of that one is exactly the same. I mean, it's 280 molecules. Well, we did not check, but you could check if you want to, as a homework example, which ones of these ones were tautomerized. So which of the column structures do differ from each other. From that one, you can know actually whether a molecule has a tautomeric form or it does not have. Then we go to the elemental analysis. We calculate the mass. So that's the first parameter. Then we calculate the log P, the log D, and all this data is is sequentially added to the set of data that we have, mass, log D, log, and so on and so forth. Okay, and then we got to the pKa, so H bond donor receptor, and so on and so forth. You can imagine that we are calculating 6 properties. The next thing that we need to do is to assign these functions that we have defined here to the molecules depending on their calculated property. Okay, how do we do that? Sounds difficult, but it's not that difficult actually. Is that we are going to load that data. We split that data depending if actually it has a mass. We compare their mass. Does it have a mass smaller than 360, or does it have a mass of bigger of 500? We know, and that's what's described in the paper published by the guys who invented this CNS MPO score, is that basically what we want to look is exactly what's in this presentation. We want to look for those molecules for which the masses are in between 360 and 500, right? So that is what we do with this rule-based splitting. The first one is that, the first split are gonna be those guys for which the rule engine are gonna just give them 0 value. Okay, so they are not interesting for us. But for the rest, actually, we are gonna have a mathematical equation that we will use to calculate the slope of this, or the trajectory of this slope here. And that is exactly this 500 minus the mass that we calculated divided by 140. Okay, that is gonna be our function. Then we have nothing else to do but to concatenate these 2 branches. So basically, we have the calculation for this one because this is, so for everything that is smaller than 360, it's gonna get assigned a value of 1. Everything that is bigger than 500 is gonna get assigned a value of 0. And in between, we have that equation that will result into this slope or into this part of the function. And if we concatenate these 2 together, then we are going to have this function in this column, okay, in the last column. And we are going to see here hopefully something different than 0. Yeah, and here you already have some values for given molecules. Wow, okay, cool. Okay, very, very similar to this, we can assign functions, these functions that you see here on the diagrams for each of these ones, okay? For each of these properties, you can calculate this function. It is really nicely described in the paper that we cited. And then what you want to do with these is basically to sum them up. Okay, you have the values for each of them calculated already, and then you want to sum these up. And this is going to be your CNS MPO score. Very good. We're almost there. What we want to do, what also is stated in the paper, is something very simple that we can do easily by a row filter, is to select only those compounds actually which are likely to be penetrating the blood-brain barrier. And for those ones, we consider those ones which have a CNS MPO score bigger than 5.0. So what we need to do is basically filter for those values, for those records where the MPO score is bigger than 5.0. This is what this node does. And if we look at the filtered ones, which naturally opens up in my other screen, we will end up with 24 only. So remember, we started with 280 and we ended up with 24 of them. Okay, where we are now. We already classified our virtual compounds. Okay, so we know that those virtual compounds that we generated, they're likely or not likely to penetrate the blood-brain barrier according to the CNS MPO score. The next step that we want to do is to switch from the virtual world to the real world. And therefore, we are going to be using another ChemAxon tool, which is called MATFAST Search. MATFAST Search is basically a search engine that is very fast in comparing molecules with regards to their similarity, like how similar they are to each other. And this service now is available for us through a web service call. That's the easiest way we can use it from KNIME, for example. And therefore, we can actually ask this service. Into this service, we loaded those 170 million compounds that are coming from enamine real, from which we know that those compounds are likely to be able to be synthesized. So they're real molecules, or even somebody already synthesized those ones. So what we want to look for is basically take one of the first virtual compound that we generated and pass the CNS MPO scoring, and look for another structure that is very similar to that one, but it's a real structure. Maybe they're duplicates to each other, so maybe they're exact matches. That's the happiest path for us. So it means that that virtual compound that we generated right now can be purchased. That would be cool, but that's rarely the case. So what we do here is basically a train of data manipulation in order to do this similarity search. Why do we need that one? Because this, so what we have is basically just a structure, right? In the first step, we are gonna, but we want really to issue a web service call with the structure, asking the service that, hey, this is my structure, give me back all of the 10 most similar structure that you have in the enamine real database. To formulate this one, unfortunately, we need to put together the post request for this one, for this call, which is a little bit, well, it's not cumbersome, but you have to do it manually. And the way it needs to look like is basically like this. This is how you can encode a request to the service. What it has in it, it's super easy because we do look into the string manipulation node, and we will see that basically we want to join the term or the string query with the encoded MI, and then we need to put there some special characters, and we have to specify the maximum count, which in this case it was 20. So give me back. This will transform the request. The structure is already here encoded. What it tells us is that I have a query. Please give me back the similar structures for this structure, and give me back the 20 most similar ones. Okay, that's what this post request says, or ask from the service. If we run this post request, then we are going to have a pretty long result, which will naturally contain that, okay, the search time was something, the target count was, as you see, exactly 171,005,001,970. So that is how big our database is that we searched against, and we see that the search time was less than 1 second. This is to be interpreted in milliseconds. This was the query, and basically this is the index of the first result that's coming back, and the dissimilarity score of this one is 0.47. Okay, if we scroll a little bit down in this, then we will see the next hit and the next hit and so on and so forth. Okay. Okay, so what we need to do is that we need to process this result, because this is not digestible for us, and actually even worse, we did not get back a structure. What is that structure? We got back only the ID of that structure. So what we need to do is basically to extract this ID and ask from the exactly same web service that, hey, give me back the structure for this given ID. And that is what's happening here during these nodes. So in this part of the workflow, I'm not going to really go into the detail there. You can check it also. So this workflow is actually available. You can download it. But basically here we have a GET request. We ask for the structure of the given ID. And here you can see that this is the ID and this is the structure that is returned for that. So here we indeed have a structure. And then, because this response is still not a single structure, but a lot of other information, we still need to select only for the smiles and extract the structure from this response, which is done basically on this part of the workflow. I really don't want to go into the detail here. This is just really data processing. So where we are now, we are here. Okay, so now we have structures, real structures that are very, very, very similar to those structures that actually we got out from the virtual screening. And we know for those virtual compounds that their CNS MPO score is a good one. Okay, so they're likely to penetrate the blood-brain barrier. And now we have real structures similar to these ones, and we would expect these guys also to penetrate the blood-brain barrier. Okay, how many of these structures we have from the real world? Let me put here 113. Okay, so that's what we start the CNS MPO scoring. Again, the CNS MPO score here for the real molecules is exactly the same as it was for the virtual ones, exactly the same workflow. I'm not going to detail it. You heard how that works. Okay, if we run those ones from 100 something, we actually reduce the set to 61. So only these ones have a CNS MPO score higher than 5. Okay, cool. So now we have, or seemingly, we have a set of real structures that are similar to those ones which virtually we generated. And then we want to know whether these are likely to be active on the dopamine D2 receptor or not. For this one, we are going to use machine learning algorithms. Not a very complicated one. We are going to use random forest. And for that one, first of all, we need to prepare a model and then apply that model to the real molecules that we filtered here in this step. How do we build a model? We take the original set that we know that they're active, right? And out of that one, you can argue whether this is the correct way of doing such a statistical or machine learning exercise. It's not the most sophisticated one, okay? You can really detail it and you can really optimize on that one. But for the sake of showing you something simple, we stuck to this one. We know that in real life, we would never use something as simple as this one. Okay, so first of all, we have to create a model. How do we do that? Well, we load all of our data, so all of our original data. Remember, it is coming from here, exactly from the model importer. And we load those ones. And what we want to do with those is that basically we look at their p-Campbell values and we classify those ones. So anything that is bigger than 7, it is considered to be active. And everything that is smaller or equal to 7, that is considered not to be active. Okay, so if we look at the output of this, we're going to see that each of these 32, a little bit more than 32 to 100 molecules is classified as being active or non-active, right? We know that they're active a little bit but some of them are not that active that their p-Campbell value would be bigger than 7. And what we do with this one, we generate chemical fingerprints, and especially we are going to use for this model ECFP fingerprint because that actually holds a little bit more information about the chemical surrounding or the biological activity of the molecule than a simple chemical hash fingerprint would do. Okay, then what we want to do is that basically we want to make a model, and for that one actually a portion of this data should go for the learner module, and we use the second part of the data to try to predict whether they are going to be active or not, but we know from the Campbell measurement whether they are active or not, so then we can compare how good our model is. So what we do is that we are partitioning our data set into 2 chunks, into 20 and 80% of that one, and we are going to be using stratified sampling, but you can draw randomly also, and so you can choose here from several options. For now, we use this one. So we put a portion of our data, we use a portion of our data to feed the model creator, so the random forest learner. We run this learner, and then we have the model, and using that model, we want to predict the rest of the data set that we have. And with that one, actually, what we are going to get is that we have the activity original, the one that actually we just classified, and this is not active because its p-Campbell value is smaller than 7, right? And then here we have a prediction of the model saying that this should be non-active. Well, cool. And the predictor is like having a confidence of 0.96, which is pretty high. So actually, and we see that this one do match. So this is kind of a good prediction. But we can also see that for exactly the second one, actually, the model was not able to predict correctly the activity of it one, because originally we classified it as non-active, but it was predicted to be active. Well, we have to give the disclaimer to the credit to the model that it is at the same time it is not really sure about this prediction. So we see that the certainty of that one is pretty low. Okay, but with this one, if we go to the score and we want to score our model, we can do the statistics and we see that the accuracy is 83%-ish. Okay, so this is already something that we can use. How are we going to use it? Well, we have the model and we are going to feed it and pair it up with the data set that's coming from the enemy real search. So what we want to achieve with this one is basically having a prediction on the enemy real set, the real molecules, that we don't know whether they are active or not. And now we are going to find it out at least on the prediction level. Okay, the workflow looks very, very similar to what you already see. We are generating the chemical fingerprints, ACFP, and we are using the predictor for that one. So we will see that we have these molecules, this 61, remember that's how many we had, and we have a prediction and we have some kind of certainty or a probability for that. Okay, what can we do? We are humans, our eyes are pretty much used to actually look at colors. We can color these ones, so we want actually sorry, I clicked the wrong thing. So we want to color all those records with green, which are predicted to be active, and all of those which are predicted not to be active to be red. So that's what actually you can see here in the output table. Red, and somewhere should be some green. Okay, there were some greens. Cool. Good. So where we are now, we are at the end of our predictor workflow. So basically, we built a model based on our original data set that we had measurements against those molecules. We built a model, and we used that model actually to predict what would be the activity of the enamine real subset that we were looking for. Okay, we can naturally visualize these ones. Sorry, I didn't mean this one, but to put it on a more interactive visualization. And okay, okay, I don't want to select. Please let me not select anything. Okay, and here you see the distribution. So here you see the compound IDs, and here you also see the CNS MPO score. And as you can see here on the legend, the red ones are the non-active ones, and the green ones are the active ones. For the sake of this presentation, naturally we used less data than Dora was using. So if I were to share you the presentation, so the whole data set, that really looks like this in reality with that set that we used. Now for the sake of this presentation, we deduced the number of molecules that we work with this KNIME node. But anyways, even here we have some molecules that are predicted to be active. So why don't we just select them? With the selection tool, we see that these are the ones. Actually, there is one red too in that one, but I don't care about that. And then what I can possibly do with this one, what I want to do with this one, is to share this one with somebody. And the way I'm going to do that is that I'm going to select here with the row filter. I'm going to filter for those molecules only which are selected. Those are basically these three molecules. Remember, one red and two green ones. And what I can do is just export it into a file. And for the file exporter, it's easy. I just need to specify my on my path where to put this SD file. And since then, I could really take this SD file and share it with my colleague, saying that, hey, this is these two or these three molecules are something that you really want to take a look at. Yeah, I can select only these two and run the filter only for those ones. And I can select only, oops, yeah, didn't I apply it? Okay, I'm sorry. Oh, sorry, yeah, and I'm executing it. And now I have only the, whoa, what's happening, please? Okay. And now I have only the two green ones. Okay. Then also owning you one more description. So with that one, actually, we got to the end of our story. We know the structures actually that we generated. We know that these are real structure and they are predicted to be active by the engine. So probably you're gonna suggest your superior or supervisor to synthesize these molecules or buy these molecules from a vendor to check for those ones. A good question is, how far did we get from our original, so doing all this kind of scaffold generation and decorating the scaffold and translating it into the real molecules. The good question raises that how far did we get with these molecules from our original space? And for that one, basically, we did a very easy test. So we calculated the similarity between the virtual compounds and the real compounds, and we plotted it on their distribution so that this similarity, be mindful here, it's this similarity in this case, so it's not similarity. So we calculated the similarity distribution to the first nearest neighbor, to the fifth nearest neighbor, the 10th and 20th nearest neighbor, showing you basically a good feel of how far we are with the real structures from the virtual ones. I think that is all that I wanted to present to you, and we are having 11 minutes to ask us any kind of questions you have, and I hope that on the YouTube stream you already did raise some questions which we are very happy to answer you. Thank you very much for your attention. And throwing back the ball to the organizers.
Thank you. Thank you, both of you, for the nice presentation as well as the demo hands-on on KNIME workflows. Being I am a regular day-to-day user of KNIME, it was really interesting to see many more features embedded in ChemAxon's and Infocomm's nodes and extensions. So we do have a few questions. I'll go through one by one. One of the question is, how do I retrieve compounds from these databases which you have shown?
Okay, that is easy. So for this database, we used only for this workflow, we used basically two databases. Both of them are public. One of them is Campbell, and you can download it in SD format or I believe even files format, or you can download it as a database dump. It is presented, I believe, in Postgre and Oracle dump. And in that database dump, you have the molecules and a lot of other associated data, amongst which data there is actually the measurement against different kind of targets. Like in our case, it was with regards to this dopamine D2 receptor. So basically what we did, we downloaded this Campbell database, and we were selecting for a target which we know that it's in context with the dopamine D2 receptor, and we extracted that data. The second database that we used for this one was the enamine real, which is also public. It is presented in SMART format. And be aware that the enamine real that we are talking about nowadays grew to 720 million or 750 million by now. So that's a fairly big database. And enamine, as a vendor, says that these molecules are likely to be synthesized and be real molecules. So these are the two, both of them are public and available for you.
Okay, great. Another question is how one could come to know that the selected scaffold is an active one?
You don't know it. That's a hypothesis. So that was one of the hypotheses that we put. Usually, if you know in drug discovery, one of the possible ways of extending your chemical space is to have the scaffold-based development of molecules, with which actually you are suggesting that you know that scaffold is active or at least plays a very, very pivotal role in the activity of the molecule, and then you want to decorate it and to optimize it. In this case, we don't know whether that scaffold is an active scaffold. That's a very, very good observation.
Okay. Another question is that will you be providing the workflows that whatever you have shown for the drug discovery participants?
Yes, Dura, help me where that is exactly on the KNIME community forum. It's uploaded somewhere.
Yes, the workflow is uploaded to the KNIME hub. Actually, we can, probably with the help of the organizers, we can distribute the link. The workflow can be downloaded, it's shared in a public folder, so we can distribute the link to that, and it contains, besides the workflow, some example data. It also contains the slides and information how trial licenses can be accessed to try the functionality. So we will ask for some assistance to the event organizers to do that and to get this info to you.
Okay. Yep. I did a basic sessions on KNIME Hub and a few other open source tools. Nodes in KNIME. So I was discussing about Hub. So it would be great if you could share the links. I'm sure Surajit will be coordinating so that we'll get to know the links there where the workflows are available. Because most of your workflows add meta nodes. So I'm not sure how a beginner who is going to use KNIME will be able to do it from scratch. So if you have some workflows already inbuilt, it would be great.
Yes, on the ChemAxon website, there are also smaller workflows focusing on parts of the functionality that we used here. So if someone wants to try property calculations with ChemAxon nodes in KNIME, we have specific examples for that as well. So we should probably include those simple ones in the information we distribute.
Okay. And the good thing is the CDAC server is already having KNIME installed in it, the version 4. So if the Surajit can put the workflows there, the people who are going to use it will be anyway having access to it. Okay. Great. So yeah, so that's all for today with the questionnaires. But if you have any concluding remarks from both the speakers as well as from Surajit, please go ahead.
Well, from my part, I wanted to thank you all that you paid attention to this presentation. It was pretty long, but I trust that it was helpful for you. So if you have any further questions, please reach out to us through the organizers and Surajit. We are happy to answer your questions. Thank you very much.
I also would like to thank you for your attention and for the organizers for making it possible for us. And yes, if you have any questions or suggestions or some cheminformatics topics that you would like to see and use in KNIME, then feel free to reach out to us. We would be pretty interested in your ideas. Thank you.
Thank you.
Okay. So great. Thank you all. Thank you all the speakers as well as the viewers, and also for your questions. I would also take the opportunity to thank the DDH training team, Virtual Toolroom, CDAC, MyGov, and other partners. And I also want to let the participants know, if you have any registration queries, please write to the email address on your screen. And if you have any issues that your email address is not getting registered, or you are being registered as an individual but cannot convert to a team, or being registered as a team but you want to do it individual, the only solution is please try to register with a new email address. That's the best solution. Please do that. And the second part is virtual tool room access has been already, I think already people have started reaching the participants so that as soon as you get back to them, you will get access to the CDAC servers as well as the softwares from the partners. So I'm sure already the activities and process has been initiated. So you will be soon getting more details about the licensing emails and other details. So that's all from me for today. Thank you, everyone. Have a great evening. Bye for now.